equation that depends on the order of the rate law, differential. If rate is equal to the change in concentration over the change in time for our reactant A for any power, that power that we deal with is known as an order. We could have a zero order, a first order, or a second order. Those are the ones that we will focus on. Now remember, on our equation page, we have a first order area, a second order, and a zero order. I threw on the calculus form for those who are interested, but again, not critical to us for chemistry. Math is just a tool. Don't tell Mrs. Milder. When I set that aside, remember we'll focus on first order and then we'll move to second and so forth. So let's begin looking at our, kind of having our equation page set aside. We'll look at what's known as a first order integrated rate law. And we'll begin by considering this equation. Suppose we have 2 units of N2O5 producing 4 units of NO2 and an oxygen. If we found that the rate is equal to K times the concentration of N2O5 in its first order with respect to our reactant. As soon as I see that first order, I now know where to focus my attention on my equation page. It's first order with respect to our reactant. And I also noticed that it had nothing to do with the stoichiometry involved with that reactant N2O5. If it's first order, we understand that the concentration doubles, the rate doubles. If the concentration were to triple, the rate would triple, and so forth. If we integrate this equation with respect to time, we get what's known as the integrated rate law. We do not need to memorize these. The equation sheet is there for your convenience. When we integrate, we get the form where ln stands for the natural log of our reactant, N2O5, at any point in time of our reaction. The natural log of the concentration of N2O5 at a point in time is equal to negative K, the rate constant, at that point in time, T stands for time, plus the natural log of the concentration of N2O5 at time 0, the initial amount provided to us. ln is a natural log key on our calculator. It is very different than log, so make sure that we're finding ln when we hit our formula. Negative, this is a dash, it's not a negative sign. The concentration of N2O5 at time 0 is given to us in data table format as the initial concentration. Our differential rate form, just to review, rate is equal to K times the concentration of A raised to the first power. However, the integrated rate form for a first order, the natural log of whatever our reactant is at any point in time, can be calculated by knowing negative KT plus the natural log of the original concentration amount. This is the general form you will see appear on your equation page. Notice that it is giving us a y equal mx plus b format, which is a straight line graph. So if we were to consider graphing this particular line, it gives us all kinds of information. I know that the x-axis represents time, usually in a second. The y-axis would be the natural log of A. I have a negative slope. That's why the negative sign appears to flip it to be positive for K. So the slope of the line is negative, the value of K. K constants are never negative, so the negative slope is flipping that to be positive if we were asked to solve for that. So if we're looking at that straight line, we could prove it's straight order or first order reaction by simply using our calculator to graph natural log of A set over a certain amount of time. We could certainly prove to ourselves that we get a negative slope that would fall into a straight line. Some people will express this reaction in terms of a ratio. The natural log and the ratio would consider the original amount of concentration over that reactant over a course of time equal KT. I don't tend to use this equation, I just wanted to show it to you. I find the one that's more useful is the straight line, y equal mx plus b format. Here's a practice. Let's take a look at our first practice. It reads, the decomposition of a certain insecticide in water follows first-order kinetics. I underline that so it just brings my mind to the part of our equation sheet, first order. It gives me a rate constant of 1.45 per years. What that tells me is the value of K. It makes sense that if it's first order, the concentration unit doesn't appear. 1 minus 1 is 0. For first order, it doesn't show up. And the temperature is 12 degrees Celsius. A quantity of this insecticide is washed into a lake on June 1st, leading to the concentration of 5 times 10 to the negative 7 grams per cubic centimeter. Assume the average temperature of the lake is 12 degrees. They're mentioning that so we're assured that the temperature remains constant and does not play a role in the kinetics. Constants, the K values, are temperature dependent, concentration independent. So we want to make sure the temperature does not influence the rate. So it's just sharing with us it did not. Question asks, what's the concentration of the insecticide on June 1st of the following year? 1 year has gone by. How much of the insecticide is left? We know it's a first-order kinetics problem, so the formula we pull out from our formula sheet, it's asking us about the remaining concentration over a course of time for 1 year. The natural log of our insecticide, I'll call A, after 1 year, is negative KT plus the natural log of the original concentration of the insecticide. Let's place in what we know into the formula, seeing that the target is the concentration of A 1 year later. The natural log of A 1 year later could be found by taking negative rate constant 1.45 per years. T in our equation stands for the time that went by. That's 1 year. Notice how I'm making darn sure that my K constant time matches the time unit I place into the equation. The K was given in a per year. I wouldn't want to put 365 days for the time. I match the unit. Plus the natural log of the original concentration, 5.0 times 10 to the negative 7th grams per cubic centimeter. What we should do is simplify the right-hand side. When I simplify the right-hand side, I'm going to need a little room down here, so I'm going to leave this space available for the next question, but I'll continue this problem down here. I'm just out of room. When I simplify this, I leave the natural log of A, what I'm trying to solve for, equal, and let's hit our calculator. Negative 1.45 times 1